In this video, we're going to take a look at integrals of parametric equations. We'll start with finding the area under a parametric curve. And so, once again, we are given our parametric equations. X is a function of t, y is a function of t, over an interval of t from a to b. The actual formula for integration is quite simple. Area is equal to the integral from a to b. And remember, again, a is the bounds of t. We're doing this in terms of t, times the function y of t times x prime of t dt. So let's just jump right into the first example. And so we are given x of t is equal to t minus the sine of t, and y is 1 minus cosine of t. And we are integrating over the interval from 0 to 2 pi. Well, the first thing that we want to do is to find x prime of t. So x prime of t is going to be equal to 1 minus the cosine of t. Then it's just a matter of plugging it into our formula. Again, area is going to be equal to the integral from a to b of y of t times x prime of t dt. And I didn't need that little extra right there. So, area is equal to the integral from 0 to 2 pi. And here is my y of t. Here is my x prime of t dt. Multiplying 1 minus cosine times 1 minus cosine of t, we get 1 minus 2 cosine t plus cosine squared t. And then going back to what we learned when we were doing trig integrals, whenever we have a cosine squared, we want to substitute in the half angle formula. So cosine squared t is equal to 1/2 plus 1/2 cosine of 2t. And then we can combine the 1 and the 1/2 to get 3/2. The minus cosine t comes down here. And then we have 1/2 cosine of 2t. And it looks like we are ready to actually integrate. So the integral, and most of the integrating that, as you're going to see, is straightforward use of the power rule, a u substitution. We're not going to get too heavy into various techniques of integration in a lot of these problems, once in a while. So the antiderivative of 3/2 is 3/2 t. The antiderivative of 2 cosine t is 2 sine t, and that's minus, of course. And then the antiderivative of cosine of 2t is going to be the sine of 2t times 1/2, and that 1/2 times this 1/2 gives us a 1/4. And we are evaluating that from 0 to 2 pi. So now it's just a matter of substituting in our values. And so substituting in the 2 pi here, and substituting in the 0, we end up with the 0 for the first term. Sine of 0 is 0, and the sine of 2 times 0 is 0, so we get all zeros here. And going through and doing the math, we end up with the area is equal to 3 pi. In the next problem, we want to find the arc length of a parametric curve. And so this is similar to the arc length formula that we already know with parametric curves. And then we have not with parametric, with a normal arc length formula is that we have a square root in it. And so the arc length is equal to the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared. And let's do our first example. So x sub t is 3 cosine t, and y sub t is 3 sine t. So first find the derivative of each one. the antiderivative, the derivative of 3 cosine t is negative 3 sine. The derivative of 3 sine is 3 cosine. Then I like to square each term. So squaring x prime of t, we get 9 sine squared t. Squaring y prime of t, we get 9 cosine squared t. And then, of course, in our formula, we have the square root of x prime of t squared plus y prime of t squared. And so all of that becomes 9 sine squared t plus 9 cosine squared t. And you can probably see what's going to happen here already. We can factor out the 9. And we are left with a sine squared cosine squared, which of course becomes 1. So this whole thing simply becomes the square root of 9. That becomes the square root of 9, which of course is 3. So our whole integration problem simply reduces to the integral from 0 to 2 of 3 dt. Integrating that, we end up with 3t. I didn't show that here. Oh, I should have put a t here. And so substituting in, we have 3 pi minus 3 times 0, which of course is just another 3 pi. I didn't notice that until I made these videos that both of these answers were 3 pi, this one and the one before it. So we now have looked at some common types of problems that we do when we're doing integration. Area under a curve, which was the first problem, finding the area under a curve, and then the arc length of a parametric curve. And so we have another arc length of a parametric curve here. Let's do this one in green. So I like to start the same way. X prime of t is 12t. That comes from x of t. And then squaring that, we have 144t squared. Y prime of t is 12t squared. And squaring that, we get 144t to the 4th. Putting all of that into our radical, which of course we want the x prime of t squared plus y prime of t squared. We have 144t squared plus 144t to the 4th. We can then factor out a 144. What I didn't show here, because I figured you guys will figure this out, is the 144t squared, which leaves me with 1 plus t squared. And then the square root of 144t squared is 12t times the radical. Well, that's what we need to integrate now. We need to integrate from 0 to 5, 12t times the square root of 1 plus t squared. Well, this looks like a perfect example of a u substitution problem. So I do the u substitution over here. Let u be equal to 1 plus t squared. du dt is 2t. And then solving that for dt, dt is du over 2t. And I showed the substituting in. So we can bring the 12 divided by 2 becomes 6. U to the 1/2 times du. And so u to the 1/2 becomes u to the 3/2 divided by 3/2 or times 2/3. Oops, I think I did that backwards here. Yes, u to the 3/2. As I'm saying it, I can see divided by 3/2 or times 2/3. I wrote it wrong. I did it correctly. I think I just wrote it wrong. All right, so yes, it's u to the 3/2 divided by 3/2 or 2/3 times u to the 3/2. Well, the 3 cancels with the 6 2 times. 2 times 2 is 4. So I actually did it correctly. I just wrote it incorrectly. My apologies. So u to the 3/2, substituting back in what u is equal to, which is 1 plus t squared. And we're evaluating that from 0 to 5. Now it's just plug and chug. We end up with 4 times the quantity 26 to the 3/2 power minus 1, which you can simplify. This, by the way, is a 6. That is 4 times 26 radical 26 minus 1. That's as good a way as any to write it. Well, we have another one. This one is a fairly easy one. I did some of the more difficult ones before the easy ones. So we have two linear equations for our parametric equations. We have x of t is 7t plus 3. So its derivative is 7. Squaring that, we get 49. Y of t is 24t minus 9. So the derivative of that is 24. Squaring that is 576. Putting those into our radical, x prime of t squared plus y prime of t squared. We end up with the square root of 625, which is 25. So that all works out very nicely. And so square root of this then, of course, becomes from 4 to 6 of simply 25 dt. So when we integrate that, it becomes 25t, evaluated from 6 to 4. And so we have 150 minus 100, which is 50. So the arc length is 50. Finally, we have surface area. We can find the surface area of parametric equations. So we now consider a volume of revolution generated by revolving a parametrically defined curve around the x-axis. So we're revolving this around the x-axis. And so this is the formula that we use. Again, this involves a radical with an x prime of t squared plus a y prime of t squared. The only difference is for the surface area is we're now multiplying it by y of t. And of course, we have a 2 pi out here as well. If you're interested in where this formula comes from, it's in the textbook. So you can take a look at the textbook and see the complete derivation of this formula, as well as the arc length formula, as well as the area under the curve formula. So we want to find the surface area generated when the plane curve defined by the parametric equations is rotated about the x-axis. And here are our parametric curves and our interval. So x prime of t is negative 3 cosine squared t sine of t. That's basically a chain rule. Okay, we're using the chain rule for that, for derivatives. And we are then squaring that. And we are using the chain rule for derivatives of this one. So sine cubed of t is 3 times the sine squared of t times cosine t. In case you don't remember where this cosine comes from, it's the derivative of the sine. And if you can't remember back to doing derivatives in the chain rule, you might want to take a quick look at a video. Just type Organic Chemistry Tutor. Has some good videos on the chain rule. Use the chain rule for trigonometric functions. And then we're squaring that. We have that. Putting them into our radical, we have the square root of 9 cosine to the 4th sine squared t plus 9 sine to the 4th cosine squared t. We can factor out of that a 9 sine squared cosine squared. And what we will be left with, fortunately, is sine squared plus cosine squared, which becomes 1. So all we then are left with is the square root of 9 times sine squared t cosine squared t. And those are all perfect squares, and I didn't need this little right there. So those are all perfect squares. So the square root of 9 is 3, the square root of sine squared is sine, the square root of cosine squared is cosine. Once we have that, remember all of that work is just to find the put a different color, is just to find this. Okay, so that's just our square root. Now we have to multiply that by y of t, which is here. And we are integrating. S is equal to 2 pi times the integral from 0 to pi over 2 times y of t times our radical simplified dt. Multiplying the sine cubed t times 3 sine t cosine t, we end up with the 3 can be brought out and multiplied by the 2 pi to get 6 pi. Sine and sine cubed gives me sine to the 4th cosine. So remembering back to our trigonometric integrals, or actually, and this actually we don't even have to do this. This is just a u substitution problem where u is equal to the sine of t. And so du is equal to the cosine of t dt. dt is equal to du over cosine t. And so in case you want to see that, that's the integral of u to the 4th, and taking out d times the cosine of t, taking out dt and putting in du over the cosine of t. Then magic happens, the cosines cancel out. We have the integral of u to the 4th du, which is 1/5 u to the 5th. And so that's basically what we've got here. Substituting in back sine of t for the u, we get that. And evaluating that from pi over 2 to 0, we have the sine of pi over 2 to the 5th power minus the sine of 0 to the 5th power. And again, I'm taking this 5 and moving it out and putting it under the 6 pi. And the sine of pi over 2 is 1 to the 5th power is 1. The sine of 0 is 0 to the 5th power is 0. 1 minus 0 is 1 times 6 pi over 5 is 6 pi over 5. And so that brings us to the end of another video. So we now know how to find the surface area generated by parametric curves being rotated around the x-axis. We know how to find the arc length of a parametric curve. And we found simply the area under a curve. So those are all typical integration problems that we've learned how to do in functions where y is defined as a function of x. And so now we know how to do those same things with parametrically defined equations where y and x are both functions of a parameter t. All right, that's it for this video.